Hello again. So the next topic is numerical differentiation. Um, so similar to numerical integration, in many cases, um, we have no choice but using numerical techniques to find the derivative of a function or derivative of certain data points that we have. So like the derivative of a function at certain point, it's the slope of the tangent line to that curve on that point. So here, like basically we want to estimate that line or the slope of that line, right? And there are different methods to do that. We're going to look at like three very basic methods to do that kind of approximation. So this is the mathematical definition of derivative, right? It's just like basically delta y over delta x, right? As delta x goes to 0, right? So like finding this limit, delta x goes to 0, it would give us the derivative of a function at point xi, which would be the slope of this line, which would be the tangent line to the curve. Right, that's what the derivative of a function is, and we want to approximate this line. We want to find another line that's easy to calculate, and the slope of the line is easy to calculate. So there is a function in MATLAB called diff. It's been overloaded, so it behaves differently depending on what kind of parameter you provide to it, or how many parameters you provide to it. One of the like if you have a vector x as the input to this function, what it does, diff x would basically give us like the result is the vector d containing the difference between adjacent elements in x, right? So if x has n elements, d will have n minus 1 elements, where the elements in D would be x2 minus x1, x3 minus x2, all the way to xn minus xn minus 1, right? If this is x, diff of x would be 7 minus 5, 12 minus 7, minus 20 minus 12, right? So it's going to be negative 32. This is going to be the result of the diff function. So we're going to use this for numerical differentiation, as you will see later. Another function that I want to show you in MATLAB is polyderivative function. So it's very similar to polyint function. For polyint, we used it for integration of polynomials, not just like definite integration, but indefinite integration. The same thing is polyder that can be used to find the derivative for polynomial functions, right? So it comes in three main or major forms. If you provide the vector of coefficient of a polynomial, then it would basically give you the coefficients of the derivative of that polynomial. If you provide two vectors, right, it would basically multiply them and find the derivative of p1 multiplied by p2. Okay, the product of p1 and p2. And if you have two inputs and you ask for two outputs, it would basically give you the derivative of p2 over p1, right? And it gives you the coefficient for the numerator and the coefficient for the vector of in the denominator. Here you see an example here, like if p1 is 5x plus 2, so the vector of coefficients is 5 and 2 as shown here. P2 is 10x squared plus 4x minus 3, the vector of coefficients is 10 for negative 3, right? If we do just polyder p2, right, it takes the derivative of p2, right? So like it would just like give us 20 and 4 as the answer. If we do polyder p1 and p2 with only one output, right, then in that case it would give us 150, 80, and negative 7, which is the vector of coefficients for P1, the derivative of P1 times P2. And finally, if we have two inputs and two outputs, it would give us the derivative of the first parameter or first argument divided by the second argument. But this is going to be in the fraction form, like it has a numerator and denominator. So it would give us 50, 40, and 23 for the numerator vector, and 25, 20, and 4 for the denominator vector. Okay, so now let's look at the numerical differentiation. Numerical differentiation is the estimation of derivative of a mathematical function using values of the function. So we don't want to find the limit, right? We just like want to use the actual values of the function to find the derivative. Three very basic categories for numerical differentiation are forward finite difference, backward finite difference, and centered finite difference. So, excuse me. So for the forward finite difference, if you want to find the derivative of f of x at xi, right? So like the derivative, the true derivative would be the slope of this tangent line, right? But in the forward derivative, what we do, we just like from xi, we go one step ahead, we go one step forward, right? So like we have xi and xi plus 1, which are far from each other, the distance h, which ideally is very small, right? So we are approximating the tangent line with this line, right? We can calculate the slope of this line because we have two data points on the curve, right? We can actually find the slope of this. It would be basically delta y over delta x, right? So these are the two actual data points that we have on the curve. So this is called forward difference. This is called forward difference. It's basically f of xi plus 1 minus f of xi. So f of xi plus 1 minus f of xi divided by h, which is our delta x, right? The amount of this is the order of the error, right? It's order of h. What does it mean? It means like if you make h 2 times smaller, your error almost gets 2 times smaller, right? So that's what the order of the error means. Similarly, we have backward finite difference. In the backward difference, if we want to find the derivative of the function at xi, we go one step backward, right? And then we use this line as the approximation for the tangent. We find the slope of this line as the approximation for the slope of the tangent, right? So this, again, it's going to be f of xi minus f of xi minus 1 divided by h, the same order of error, right? Again, it means like if you make h 2 times smaller, your error gets almost 2 times smaller. Like this is like order of magnitude. It's not very exact. Another method for numerical differentiation is centered difference. So in centered difference, again, if you want to find the we want to find the derivative of a function at xi, we go one step forward and also we go one step backward. So we find f of xi plus 1 and f of xi minus 1. If we connect them, like there's a line here, and we use the slope of this line as the approximation for the slope of the tangent. So this is going to be f of xi plus 1 minus f of xi minus 1 divided by 2h, because we went one step forward and one step backward. That's why we have 2h here. Okay, so this centered difference is generally more accurate than forward and backward because it uses both future values and past values of the function at xi, right? So because of that, it's generally more accurate. Not all the time, but generally more accurate. And the order of error for this one is order of h squared, right? What does that mean? It means like if you make h 2 times smaller, your error gets 4 times smaller, right? So that's another advantage of centered difference. There are other variations for forward difference, also the same for backward and centered difference. This is the general formula, very simple formula that we use for forward difference. In this case, the order of error is order of h. But instead of using only 2 data points, you can use 3 data points, right? If you do that, then our formula becomes this, right? And in this case, right, like you need to do more calculations, so your the energy or the effort that you have to put to find the numerical derivative is going to be more, but your answer becomes more accurate. Also, the error for the order for the error becomes order of h squared. So it means that, like, again, like this is more accurate, more precise than the original formula, right? But this one is like only for your information. The same way that we can calculate first derivative using forward difference, we can calculate second or third or fourth derivatives as well, right? So these are formulas for second derivative, third derivative, fourth derivative using forward finite difference. The same thing applies for the backward finite difference. You see that, like, there is another variation of backward finite difference that uses 3 data points, right, to calculate the slope, or like the slope of the tangent, like approximate the slope of the tangent or find the derivative of the function at xi. And if you use the second formula, the order of the error would be order of h squared. And similarly, we can find second, third, fourth order derivatives as shown here. And the same is true for centered difference. In centered difference, the original formula provides the order of h squared for the error. There is another variation that uses actually 4 data points, 2 forward, 2 backward. And if you use this one, the order of error, it's going to be order of h raised to power 4, right? So it gets more accurate, but again, like, it's a compromise between the effort versus the accuracy. For like calculating the derivative or numerical differentiation using MATLAB, we can use 2 functions, diff and gradient. So you remember that the diff function, if you provide a vector, it provides the difference between adjacent elements, and that's exactly what we need for forward and backward difference methods, right? So like for forward and backward difference, we can take advantage of this function. We can find def y and divide it by def x. This is an element-wise division, right? We're dividing every element of this vector by this vector. So that provides the, that provides the backward or forward difference approximation. Now let's look at this one. So here we have our x, which goes from 0 to pi with the step of pi over 50. So our h is pi over 50. And this is our y, right? It's a sine function, but also has some noise, random noise. Okay, so we actually can't find the analytical derivative of this function because, like, this is like, it has a random component to it. Okay, so d1 is defined as diff of y element-wise division by diff of x. So we find the difference between every adjacent y and every adjacent x, and we divide them together, right? So that's going to give us the backward difference estimate. I'm going to show you that this is also the forward difference estimate as well, but for different points. I'm going to talk about it a little bit later. The same, like using some vector manipulation, we can also do centered difference, right? So for centered difference, like this d1 is now basically derivative of this function at every single data point, except, right, is if you're applying backward difference, you see, like in backward difference, we need to go one step backward, right? If you're at the beginning of the interval, right, there's nothing before that, right? So we can't apply backward difference at the beginning terminal or like terminal point of the interval, right? So we can't apply backward difference here. The same thing is true for forward difference. We can't apply it at the last point because we can't go one step forward. We don't have any data. And for centered difference, we can't apply it like on either of the beginning or end points. So here, if we apply this formula, it would give us the backward difference, right, for every point other than 0. For every point other than 0, right? Because it can't apply backward difference on the first point. Okay. So then the next point after 0 would be pi over 50, right? So we would find the derivative at that point, and then 2 pi over 50, and so on. It can go on. This also gives us the derivative for every point except the last point using the forward difference, right? So this actually gives us both backward and forward difference estimation, but for different points. One of them goes from the second point all the way to the last one. That would be the backward. And the other one goes from the first point to the second last point. That would be the forward. And for centered difference or central difference estimation, we can't apply it on the first or last point, right? So if we basically have n points, we can only find the derivative at n minus 2 points. And how we do it, right? We basically go one step forward and one step backward. So that's why it's showing here like n and n minus 2, n and n minus 2, and we just do the division. Right? It also like goes from, right, because like we can't, you remember in MATLAB indices starts from 1, right? So we can't find the centered difference approximation at the first point, right? So that's why this one, right, it's gonna be if like you just like ignore the rest of it, it just like look at y3 minus y1 divided by x3 minus x1. That would be the centered difference formula that would give us the derivative value at x2 at the second point, right? You see, like we go one step forward from 2, we go one step forward, and we go one step backward, we find the difference, right? And this can go on from 3 to n, and like 1 to n minus 2, and the same thing here, right? So it would give us the central difference estimation of dy over dx for all the points except the first point and the last point. Okay, so like the forward difference formula would be exactly the same, right? But you just like have to interpret it differently. Like if they ask you like what is the derivative of this function at x equal to 0 using backward difference, you should say like we can't calculate it using backward difference. I can calculate it using forward difference, and it's going to be the first element of this vector d1, right? The same thing is true for the last element's derivative, the last x derivative. Like if they find the derivative of this function at x equal to pi, you can't apply forward difference. You can't apply center difference either. you can only apply the backward difference. Okay, so you can also like plot the results and compare like the results for all the three methods. So there is another function for differentiation in MATLAB called gradient. Determines the derivative of the data in f at each point, right? So it doesn't have any limit. How it does it? It basically applies forward difference on the first point, because we can't apply backward difference or center difference on the first point. So it applies forward difference on the first point, backward difference on the last point, and center difference on all the inner points. Okay, all the inner points. That's how it would calculate the derivative of a function. You can provide a function handle. You can provide a step. If you don't provide it, it would use step of 1, which is not very accurate. The same function can be used to calculate partial derivatives, right? So like this is not part of your course, but like you can, like in your future courses, you might want to use this in certain assignments or questions. So this is another example, right? X goes from 0 to 2 pi with a step of 0.01. Y is sine of x, right? We can calculate def y by def x, right? This is going to compute the, as def computes the first difference, and this is going to give us the either a forward or backward difference, like depending on how we look at it. This part is also for your information, right? So def can also operate on matrices. Right here we have a matrix 1 2 3 4 5 4 8 6, right? And derivative of the matrix, you can just like apply the def function on this matrix with 1 and 2. So first difference of mat along the second dimension. That's what this means, right? First difference of this matrix, first difference of this matrix along the second dimension, right? So it's going to be given like this. You see like 3 minus 1, it's 2, 5 minus 3 is 2, 8 minus 4 is 4, and 6 minus 8 is negative 2. You can see help for more details. The opposite of def is the cumulative sum, that it would just like add the adjacent elements, right? So that can be used in other applications. So this is like also 2D gradient, like you can like find like the same way that like this applies, the diff function works on matrices, the gradient also works on matrices as well. So here you see an example of the numerical differentiation. This time we are not using any of the built-in functions in MATLAB, but we are actually using a function handle, right? And using the exact definition of derivative, right? This is the exact definition of derivative. If you want to find the derivative of this function, right, it's going to be f of x plus h minus f of x divided by h, right? So that's the definition, right? Like where h goes to 0, where h is a small number. So here we just write a function, like a two-variable function with respect to x and h. You see that this part is f of x plus h. Right? You see like you replace x with x plus h. And this one is f of x. So this is f of x plus h minus f of x divided by h. So it's a function that depends on x and h. It's a two-variable function. We want to find the derivative of this function at x equal to 2 with this much time step, where h is equal to 10 to the power negative 4, right? So if you do that, we just like can find the value of the function at all the points between x changing from 0 to 8 with the step of 0.01. Like instead of just calculating one derivative, we can calculate the derivative at all the points with another h. Like it can be it shows like basically here one time you're choosing 0.1 as the step, one time we choose 0.01 as the step, right? And you see the difference, right? This one should be more accurate. As you reduce the step, as your time step or time sample gets smaller, your accuracy goes higher. This is what I just mentioned. Like you can just reduce the h. As you reduce the h, your error gets smaller, but there is a limit, right? For the smallest value of the h, any computational software, any programming language, it would have a limit on the amount of accuracy that it can have for double numbers, right? Computer, it's not an analog device, right? It's a digital device. So right, there's just like a certain threshold for the smallest h that you can have, right? So that's why it says like there is a limit. Excuse me. This also shows the again, this slide is for your information because this is multivariable calculus, but this shows an example of gradient, and one of the nice plots that you can have to show the behavior of a function is using these arrows. It basically shows like how fast or how slow the function is changing and in what direction. So the direction of the arrows shows like the direction of the changes of the function. Also the length of them shows like the value of the changes, right? So this is like done using the quiver function and the mesh function. Like the plotting is done using those functions, and the derivative is found using the gradient function. One thing that you should pay attention to is that integration tends to make the curve smoother. If there is some error in the original curve, like if you take integral, you just basically smoothen out the error. But if you're doing numerical differentiation, like if this is our original function without any noise, like you take the derivative numerical differentiation, you find it right there, like that. It's perfect. But if your function has a small noise, right? Small noise, you see like one point is slightly higher than where it should be, right? The numerical differentiation amplifies it. Right, so like you see like what happens if we take derivative of this one numerically, you see like how different it becomes from what it should be. So a shortcoming of numerical differentiation is that it tends to amplify errors in data, whereas integration tends to smoothen the data errors. Another topic that I have to cover for this lecture is root finding, numerical root finding, right? So we want to find the zero crossing or the intercepts of a function, right? That's basically the values for x that makes f of x equal to 0. Those are called the roots of a function. What we use a method called bisection method, right? So like we're gonna use the bisection method. Let me just go back to where it was. So a simple method for obtaining the estimate of the root of the equation f of x equal to 0 is to make a plot of the function and observe when it crosses the x-axis. So this is one way of doing it. But one thing that we can observe from here is that if we have an interval and if we know that we have a continuous function, right, a continuous function like without any discontinuity, right, there's no discontinuity, it's a continuous function, if we have a continuous function and if we have an interval, if we look at the value of the function at those terminal points of the interval, if they have the same value, we can't say anything about like this function having a root in this interval or not. It might, right? It might have no root, or it might have multiple roots, or it might have even like just one root if it's like tangent to the x-axis. But look at this case, like if at the both ends of the interval the values of f of x have opposite signs, right? One is negative, the other one positive, or it's positive or negative, right? So this function is continuous, right? So it was somewhere here in the negative half plane, right? And at this point it's on the positive half plane, so like it has to get from here to here. It's a function and it's a continuous function, so it can't go from here to here, or it can't just like be discontinuous, right? So it means that it has to cross the x-axis somewhere in between at least once. It might cross it like multiple times, but at least crosses it once. So this observation is what we use in one method to find the root of a function. So again, like this is a numerical method for root finding, and we're gonna like see two different methods to do that. The first method is called bisection method. We have an interval, right? This, like if you're familiar with binary search, it's very similar to that. It's very similar to that. So we have an interval, like the original interval a1 and b1. So first we find an interval a1 and b1 in which f of a1 and f of b1 have opposite signs, right? Here, like f of a1 is positive, f of b1 is negative, right? According to the, like this is like very trivial, but it's also called intermediate value theorem. If we have a continuous function and an interval that at the end points of the interval f of a1 and f of b1 have opposite signs, according to the intermediate value theorem, somewhere in this interval, somewhere between a1 and b1, there should be a zero crossing, there should be an intercept, right? So what we do, right, we try to make this interval as small as we want, right, based on the threshold that we want to have for our like error, right? So how close we want to find the root of the function. So here, like you see that like a1 and b1, so what we do, like we know that there is a root here between a1 and b1, right? So we basically, using the bisection method, bi means two, right? So we divide this interval into two sub-intervals. We calculate the f of the midpoint. Here, let's call it b2, the midpoint. So f of b2, it's negative, right? F of a1 is positive, f of b2 is negative, so we know that the root has to be between, there is a root, at least a root between a1 and b2. So we do this again. We divide this second interval into two sub-intervals and we find the midpoint value, right? So like here, like b2 was a1 plus b1 divided by 2. Here, if we have a2, it's going to be a1 plus b2 divided by 2. And we find f of a1. We find the value of the midpoint, the new midpoint. Here, it's positive. F of a2 is positive, f of b2 is negative, so we know that our root, there should be at least one root between a2 and b2. And we keep doing this. We keep doing this until our interval gets as small as we want, right? So we eventually gonna find the root, right? It's not very fast because each time we get like only 50% accuracy with each iteration. Like our interval gets like 2 times smaller, right? It's not very fast, but it's guaranteed to find the root, right? It always converges to the root. So this again shows you the this graph shows you like how bisection method is done iteratively. First iteration, like we have x1 and x low and x upper, right? They have opposite, like f of xl and f of x up, xu, they have opposite sign, right? We divide it by 2, right? So like here we find the midpoint, f of xl, f of the midpoint, it's negative, right? This is negative, this is positive, so now our interval is this one, xl, x up. Again, we find the midpoint. The midpoint, it is positive, right? So we know that our root has to be between these two ends of the interval, and we keep doing it. We keep doing it. The error is reduced by a factor of 2 at each iteration, right? So like basically this L and U, XL and X sub L and X sub U get close to each other until like this interval is small enough, right? Small enough that we can say that, okay, like our root is here, right? X and XL and XU are very close to each other, right? This is a MATLAB function that implements the bisection method, right? So we take a function, right? And like here, like this is like the function handle that we have, and we always like given, we are always given 2 points on that function that f of a and f of b have opposite signs, right? So like this is like the 2 points that the function takes as parameter, as input. We also like say that like we want to find one of the roots with this much error, okay? So it means that we are gonna continue dividing the interval into 2, right? Into 2 until the point that either f of a or f of b, both of them, right? Like at the root, f of a should be 0 and f of b should be also 0, right? If you have the root, right, at the root, the f of the root is equal to 0, right? But here it says that like instead of getting to 0, like even like 10 to power negative 10 is good enough for us. So we say that continue doing this bisectioning until both f of a and both f of b are actually should be less than or equal. Oh, sorry, like we keep doing this as long as these are bigger than or equal the error, right? As soon as it becomes less than the error, then like one of them gets less than an error, like we are going to be out of the loop, we found the root. Another way of interpreting the error, we say like, okay, as like continue doing this until the point that the length of this interval gets smaller than a certain threshold. That's another way that you can interpret the error. So here the error is interpreted as the value of the root that ideally should be 0, but we stop at a certain point because otherwise like we would never get like to exact 0, right? It's gonna take like infinitely, right? Like we say like, okay, like this much error is tolerated, so this is our threshold. You can also interpret the error as the length of this interval. We say that, okay, we're making XL and XU close to each other. If they're close enough, then we stop. Okay. So this is an example for you to work on. We have a function, we want to find the root. F of 1 is -1, so it's negative. F of 2 is 8 minus 2 minus 1, so it's 5, it's positive. So we know that there is at least one root between 1 and 2. Okay, we want to find it with this much threshold, right? So you can either like use this function, right? Or like if you want to do it on hand, like you can also like keep doing like the first few iterations, but you can also like apply this function, right? That is very easy to do, like based on your programming knowledge. Like it's like very similar to, you see, like it's very similar to binary search. We are dividing the interval, the search domain, into two sub intervals, and like we just figure out which side, the left side or the right side, we should focus on, right? So you can use that function to find the root of this function between 1 and 2. Another method that we have to find the root of a function, it's called Newton method or Newton-Raphson method. This method needs an initial guess. Right? So let's say that we want to find, it doesn't have to be very close to our root, but like it just like basically has to have an initial guess. And the choice for x null or x sub 0, it's sometimes it's going to be very important, right? Sometimes if your choice is very far from the root, then you might not converge to the root, right? Or you might converge to another root than like the one that you were looking for. So in this method, which is an iterative approach similar to bisection method, which is an iterative approach, in this one you have an initial guess, let's say x0, right? Based on this formula, right? So if this is, let's call this one xn, f of xn, f prime of xn. So we say that xn plus 1 is x of n minus f of xn divided by f prime, or derivative of xn, right? So if this is x0, if we start from here, we say that, okay, like this is like, this is our first guess for our root. Then we find the second point based on this formula, and then again we put this point into the formula again to find another point, x2, and then we do it again, like to find x3 and x4 and x5 and so on. So the formula that we use here, it's going to be like this. We have an initial guess, and we would just like basically say xn plus 1 is equal to x sub n minus f of xn divided by f prime of xn. This method not only uses the value of the function, but it uses the value of the derivative of the function. So we also have to have the derivative of the function to use Newton method or Newton-Raphson method. So it converges faster. If it converges faster than the bisection method, right? Because it just like uses more information, right? And you see like it gets closer to the root by a factor bigger than 2, right? Which was the case for bisection method. However, it doesn't converge all the time, or it might not converge to the root that you have, like that you have in mind. You might, like your function might have 3 different roots or 5 different roots, and based on your initial guess, you might converge to like one of them, right? And that one might not be the one that you wanted to find. Okay, so this is again, this is showing the formula for finding the iterations of Newton-Raphson method. Okay, the con or disadvantage of this, like for some functions, this shows like slow or poor convergence, or it might not converge to the root that we want to get based on the initial guess for your x0. Again, I implemented this function using MATLAB. So this is like showing you the Newton's method solution. Like it shows that this is our function, right? Like we also needed the f prime. So this is our f prime. And this is the implementation of the Newton method, right? Right. So here, like we say, like the new point is going to be the old point minus the function value at that point, at the old point, divided the derivative value at that point, right? And again, we keep doing this until the value of f of xi, right, at the root is supposed to be 0, right? But we can keep doing it until it gets smaller than a certain tolerance value or threshold value. So here our tolerance is 10 to the power negative 6, the convergence tolerance. And here it shows you that like even like after like only like 6 iterations, only after 6 iterations, we find the root of the function. You see like the initial guess that we had was 1. The value of this function at 1, it's like given here, right? So like here, like it's given here, right? And then like you see like how it goes to 0 so fast. Newton-Raphson converges much faster than bisection method. While the bisection method is very robust, it means like it converges all the time. Newton-Raphson might not converge in some cases, right? Depending on the choice of your x0, or sometimes let's say like if your the derivative might just like be infinite, right? Like it might just like be very close to infinite, right? For some functions. So like it doesn't work all the time. So I mentioned for polynomials, we can find the indefinite integral using the poly_der function. We can find the derivative using, you can find the integral using poly_int function and the derivative using poly_der function. And we find the roots using the roots, right? So we provide the vector of coefficient and we can find the roots of a polynomial. Okay, and if we have the roots, we can find the polynomial coefficient using the poly function. So for the polynomials, we've seen like many functions: poly, roots, polyval, poly_der, poly_int, right? There are many different functions for polynomials. Okay, so this is an example for you to find the roots. You can also like try like poly_der, poly_int for all these functions as well. So here, like you want to solve, like you want to find the root of, you want to find the square root of 2, right? You want to find like what's the value of a square root of 2, right? The square root of 2, it's going to be the solution for x2 is equal to 2, right? So your function is basically x2 minus 2. You want to find the roots of that function. You can use the bisection method, like using these two end intervals, like end points, and you can also like you just like keep going until like your error becomes less than 0.05, right? So this is an exercise for you to work on. You can use the sample code that's given. Now, as the last topic, I want to mention about a toolbox in MATLAB that you can use for finding the derivative, integration, root finding. It's called symbolic toolbox. Symbolic toolbox. So it's an add-on toolbox that you should install when you install MATLAB, or you can install it later. But right, if I just like use like in my like MATLAB work window, if I say that a plus a, right, it would give me an error because it would think that a is a variable or is a vector that's not defined, and I haven't used it. Right? It can be also the name of a function that is not defined. But there are two keywords that we can use to let MATLAB know that we want to use this as a symbol, right? It's not a variable, it's not a vector, it's not a function. We want to say it's a symbol. So we can use the sim function or the sims function. Like if you use sim, like you need brackets. If you use sims, you don't need that. So if we do that, if I say a plus a, it would give me 2a. Okay, and if I use the sim function, I can just like define functions with respect to x, and like this is not a vector, it's a symbolic function, right? If you see that like if we have a symbolic toolbox, and if I define x as a symbol, I can solve equations, right? Using the solve function, I can solve equations. Okay, there are So like you can see that here, this is a symbolic expression, right? For a polynomial, like if here, like look at this one, right? X is a symbol, so this is a symbolic expression which happens to be a polynomial, right? If I want, I can use the sim to poly, like it basically means symbolic to polynomial function, to turn this one into the vector of coefficients, right? So like you have sim to poly function to convert this, the format of this expression from symbolic to just a polynomial. Basically, like PV now becomes the vector of coefficients. Instead of like being a symbol, becomes a vector. Okay, we have another one called poly to sim, right? So you can, like, if you have the vector of coefficients, you can turn it into a symbolic expression using that one. It's actually shown here, poly to sim, sim to poly. So what is the application of the symbolic toolbox in calculus? All right, so like as I mentioned, diff has many applications. It's a function that's overloaded, so it can behave differently based on what input you provide to it. So if its input is a symbolic expression, so here we say that we wanted to define this function, we did it symbolically. We say x is a symbol and f is a function of that. This is an expression, a symbolic expression. The diff function would take the derivative of this one, right? The general derivative formula, right? Doesn't have to be the derivative at a certain point. It actually gives us the actual formula, right? You can find it at a certain point if you want as well, right? So later on you can define it as at a certain point as well. The same thing, like we can use diff to find the derivative. You can use int, short for integral, to find the antiderivative or the indefinite integral, right? Indefinite integral. You remember that using numerical methods, we couldn't find indefinite integral. We could only find definite integral. Means like only the area below a curve. But using the symbolic toolbox, we can also find the indefinite integral of a function. You can also find the definite integral, like if you add the limits, the lower and upper limits, you can find a definite integral as well. You can also, like, there's a function called limit that would basically give you the limit of a function when h goes to 0. So like int, diff, limit, there are many, solve. These are like all the functions that you can use in the symbolic toolbox. Some examples here, like it basically asks you to find the integral and compare it, like maybe with the symbolic toolbox using like different methods. Like here, like this is like from the symbolic toolbox, and like this is from the trapezoidal rule, so I can compare them. And this is also like a wrap up for everything that we've seen. Like for differentiation, we saw like numerical differentiation using centered, backward and forward difference, use the symbolic toolbox, and we also like saw that we can, like for like specific functions called polynomials, we can use the polyder function as well. These are review of all different functions that we saw, or like all different concepts that we saw in this series of videos. These are the references, and thank you so much.